This is Introduction to Structure Lesson 6, Bending Moment Diagrams for a Cantilever Beam. So just let's remember that for bending moments we have two possibilities. We have sagging moments when we have the situation, the external load bend the beam in this way, producing compression on top of the beam and tension at the bottom of the beam, and this is considered a positive moment in our convention. The second possibility, and the only two possibilities are those, the hogging moments, when the external load produces a bending in the opposite direction, producing tensile forces on top of the beam and compressive forces at the bottom of the beam, and this is considered negative in our convention. So we have this cantilever beam in here where we have determined already the reactions, the reactive moment 105 kilonewton per meter and the vertical reaction of 50 kilonewtons at the point A where we have a fixed support. This was done in previous lessons. So we have now a beam which is in equilibrium under the load of 10 kilonewton per meter and an UDL that is a length of 3 meters as you see in the screen. And these punctual loads of 20 kilonewtons apply in the middle of the cantilever beam that have a span of 6 meters. So in the first place we're going to read the definition of the bending moment. The bending moment at any section of an structure is equal to the summation of moment to the left of the section or to the right with the opposite sign. And we are going to see exactly what this means in the coming examples. So reminding this definition, we're going to do the calculations. In the first place, we are going to analyze the first section, which is a cross section, which is immediately after the point A, where we have applied the reaction 105 kilonewton per meter. So the left side of the structure in this case is the structure that is inside this green frame, in this green rectangle in here. So the only forces we have at the left side of the structure of the beam are the moment of 105 kilonewton per meter and the reaction 50 kilonewton per meter. The only moment we have then is 105 kilonewton per meter because the moment produced by 50 kilonewtons around this cross section is 0 because the perpendicular distance from this cross section to the force is 0. So when we write the moments to the left at this cross section A, we found that the only moment we have is 105 kilonewton per meter, and this moment is negative because it's anti-clockwise and is negative in our convention of moments we introduced it before in first lessons. This is a hogging moment, so it's producing this sort of deformation, so it's negative definitely, and there is a consistency between all the convention we have included in these presentations. If we do the calculation of the same moment at the same cross-section but considering the right side of the structure, the right side of the structure includes all what is inside this rectangle in blue. As you see, in this rectangle we have the UDL and we have the punctual lobe of 20 kilonewtons, but we don't have the moments because the moment is to the left side of the structure and we don't have the reaction because it's on the left side of the structure as well. So we write the equation to the right side of the structure. We start with a minus because the definition says with the opposite sign. So we put the minus, we open the brackets, and we have 10 kilonewtons per meter multiplied by 3 meters, the whole UDL, multiplied by 1.5 meter, which is the distance from the equivalent load in the middle to the point A. And this is the positive moment produced by the UDL to the right side of the structure. The positive moment produced by 20 kilonewton is 20 kilonewton multiplied by 3 meters, which is the perpendicular distance to the cross-section A we are analyzing. And when we run the calculation of this simple equation, we found that the moment is again the same value, minus 105 kilonewton per meter, which is consistent with our convention and is consistent with the definition of moment. So this moment calculated to the left side of the structure or calculated to the right side of the structure have the same value, 105 kilonewton per meter, and is negative. Now, if we consider the cross section 1, the left side of the structure is what is inside the rectangle in green. So now we have the moment, we have the reaction, 50 kilonewton, and we have certain distance in here. We have 1.5 meters from the force from the reaction to the cross-section 1. And we have this portion in blue in here of the UDL acting and producing a negative moment, because we are going to have an equivalent load in the middle of this rectangle, this half UDL, and multiply by 0.75 meters to the cross-section 1. And this is what we have in here written in terms of the moments at the cross-section 1 to the left side of the structure. The first moment we have is minus 105 kilonewton per meter, plus the moment of 50 kilonewton, which is the reaction, times 1.5 meter, the distance from here to here, and minus 10 kilonewton per meter times 1.5 meter, which is the equivalent load to the UDL, and multiply by 0.75 meter, which is the distance from the middle of the UDL to the cross-section 1. Running this calculation, we found that the moment at the cross-section 1 is minus 45.25 kilonewtons per meter. And this is the case, this is a Hawking moment as well, so it's negative. We can do the same calculation considering the right side of the structure. So now on the right side of the structure we have half of the UDL, and we have 20 kilonewtons applied in the middle of the structure, and we have the distances. We are going to write the equation to the right side of the structure. We start with the minus with open bracket, and we have 10 kilonewtons per meter times 1.5 meters is the equivalent load of this UDL, multiplied with by 0.75, which is the distance from the middle to the cross-section 1, is positive because it's close-wise, so positive in our convention, and plus 20 kilonewtons times 1.5 meters, which is the distance from 20 kilonewtons to the cross-section 1, where we are doing the calculations. Calculating this simple equation, we arrive to the same value as before, minus 41.25 kilonewton per meter. So consistency again. The value of the moment to the left or to the right has to be the same in value and in sign. This is Hawking again, so it's a negative moment definitely. If we go to the cross-section 2, the left side of the structure now includes the UDL, the moment, and the reaction 50 kilonewtons in the at the fixed support. So to the left of the structure we had minus 105 kilonewton per meter, the reactive moment, plus 50 kilonewton times 3 meters, because the distance now is from here to here is 3 meters, and minus 10 kilonewtons per meter times 3 meters is the equivalent load of the whole UDL, multiplied by the distance from the middle to the cross-section 2, which is 1.5 meters. If we do that, we arrive to the conclusion, or our calculations tell us that there is a moment equal to 0 kilonewtons per meter at the cross-section 2. And it's a Hawking moment, but it doesn't matter in this case because it's 0. If we do the calculation to the right side of the structure, it's consistent again, and it's clear that to the right side of the structure from the cross-section 2 there is nothing producing moment, so evidently the moment is equal to 0. Now you have to prove, considering doing the same consideration we did for the other cross-sections, you have to do by yourself the calculations of the moment at the cross-section 3 and the cross-section 4, and you will realize that these moments are equal to 0 as well. So, we have the resuming here all the values of the moments for this cantilever beam. So the moment at A is minus 105 kilonewton per meter, at 1 is minus 41.25 kilonewton per meter, and moment at 2, 3, and 4 is equal to 0. If we sketch the diagram, we are going to realize that this is the distribution of the moment. The moments are sketched on top of the reference line. In this case, is the opposite as we did in the simple supported beam, because in this case the moments are negative. The other thing you will realize if you will run calculations in additional points, additional cross sections, for example in here between A and 1 and between 1 and 2, you will realize that the distribution of the moment is parabolic. And this is what happened when we are under UDLs, if you remember from previous examples on previous lessons. Every time you have in UDL. Under the UDL, the distribution of moment will be parabolic, and this is the case as you can see in the bending moment diagram. So this is the bending moment diagram for this cantilever beam. So I have a parabolic variation from -105 to 0 from 8 to 2, and it's 0 from 2 to 4. In the whole beam, we have hogging bending moment, which is negative. Thank you.